I'll come back and let them in. Right. So the lecture today is about mechanical energy storage. We talked about mechanical energy storage already, which is pumped storage. Pumped storage is also a mechanical energy storage. Maybe compressed air is also a mechanical energy storage, but you also have the thermal component, which takes 20 to 40% of the efficiency of the system. So it's not 100% mechanical. It also has to do with thermal storage. So I'm going to go through the other mechanical energy storage technologies. I'm going to talk about flywheels, energy storage, solar power and flywheels, grid inertia, gravitational energy storage, and underwater energy storage, which are the main topic, which are the main topics for mechanical energy storage. Flywheels is not this flywheels because I put flywheels in the research bar. Give me these toy, so not this flywheel. It's also not these very old mechanism used in order to provide a constant supply of energy for people that used to tricotar. But these flywheels, they were already used in the past, several cultures, in order to improve the quality of energy services for different services. In this case, is for producing tecidos, right? To produce closes. So the idea is that you would step in this mechanism, which would give some strength for the wheel to start turning, and then the wheel will turn and continue turning, and then you have to step again. So you can you could in the past produce a constant amount of energy in order to give you the a linha, yeah, required to produce the closes in the past. Another use for flywheels in the past, since ancient Egypt, was, for example, pottery wheels. So also the energy was produced maybe from hydroelectric sources, which was not constant, which had issues, and you needed a constant supply of energy for your service. So they wanted to make sure that they wouldn't destroy the parts in order to because of variations in strength in the spinning of the discs. So they have these very heavy discs. Also, for example, for the production of grains, they also use these discs in order to produce a good quality energy service in order to produce to grind grains. But what we're talking about in this lecture is the modern version of flywheels, which is this device, which you can see in the right of your screen. And it's a cylindrical form where you have a chamber that makes sure that if you have an accident, for example, it's contained because the metals they turn at speeds of more than 1,000 rotations per second, um, more than 1,000 rotations per minute, and the strength, the shear that it goes through these metals, it can break the material that's spinning. So you need this security cover in order to protect people outside if it blows up. The other reason also because you need to create a vacuum here, so you have to have some location where you can extract the air from inside. And the idea of creating a vacuum is that you reduce the friction from the spinning rods and, and the air inside this chamber. There are several approaches in order to spin the metal. I'm going to go through more in detail, but you have, for example, magnetic lifts in order to suspend the weight of the material and reduce friction, because if it's not suspended magnetically, you have to have, for example, physical form in order to hold, in order to maintain the weight of the heavy material, which of course spinning at very fast rates, this causes issues with the equipment, and you have to have very high lubrication costs, very high maintenance costs. So basically, the idea is that this rod inside is going to spin, and the faster it spins, the more energy stores. And depending on the shape of these metal materials, you have the amount of energy that you can store within this flywheel. I'm gonna show you some shapes. The next slide, which dictates the Q. So the E is the specific energy is equal to the total energy divided by the mass of the rotor. And this E divided by the mass is equal to the K, which depends on the shape, and the ultimate strength of the metal. So the strength of the metal would dictate how fast it can spin. And the faster it spins, the best, because you store more energy. Some materials, if you spin too fast, they're just going to break after some minutes because they're not strong enough not to collapse. And this pi is the no, it's not pi. Sorry, this is the density Greek symbolus is the density of the material. So this is the equation in order to see how much energy you can store with these rods, and the energy that you are storing while it's spinning varies with I, which is this equation, apart from W, and W is the rotational speed. So the amount of energy that this device stores is proportional to the rotational speed. So this technology is not that technology that you can, for example, scale up like wind. For example, wind power. The bigger that you make this, you can make a huge, the size of a huge building. Is not going to lower the cost exponentially because of this ultimate strength value. Because the ultimate strength value, if you have a material is very big, the further that you get, the higher the speed, because the closer that you are from the spinning axis, the lower the speed. But the further away you are, the higher the speed, and this limits the amount of speed that you can get, because if not, the material breaks. But of course, there is a lot of improvements in the future that can improve materials. So this ultimate strength can increase with new technology, new materials. For example, carbon nanotubes or graphene. other materials in order to increase this strength, and then will substantially increase the efficiency and reduce the costs of the system. Any questions about the theory? Hello. Yeah. So the standard for K value is based on this shape, but it's so this shape here, which is kind of a disc, which they assume that is the best shape, because the further that you go along, the more stress you have. So shaping it like this, the speed uh, of the spinning rod makes it, I guess, it reduces the chances that it's going to break after several uses for energy storage. Then you have several other ones. The ones that has been mostly used nowadays is this thin ring. So the most of the weight is located as far as possible from the center of gravity, which so the further that you are from the spinning rods, that the higher is the velocity, and the further that you get, the more energy you store. So probably this is the reason why they're using this conformation. Flywheels. So what are the advantages of flywheels? They have fast charge capability. I'm gonna go talk a lot about this. Long life cycles. If you have a good design that is not going to break, and the shear strength is well calculated, and you don't surpass a given velocity, it can work for several cycles. They have high power density. This is the power density is as high as a battery, for example. Not top quality batteries, but it can be compared to maybe to so today you have energy batteries of 200 kilowatts hour per kilogram, and this is something like 60, so 4 times smaller. They used to have buses, for example, in the past that they used to use flywheels in order to make short trips and then connect to the grid, and very quickly with a high voltage you can increase the spinning of the flywheel. So they were used in transportation, which is very interesting. Also, I didn't go so much in detail because no one ever is going to use it again, because batteries are already much better than flywheels for transportation. I'm not going to spend so much time on this, but it has been used several cases in the past. These flywheels in order to for transportation of buses, trains. Low maintenance requirements, particularly if you have the levitational technology. The state of charge is easy to determine through rotational speed. So you know how much the device is charged by knowing the speed of the, which is not always easy, but to know how much a battery is charged, for example. The wide operation experience, it's a mature technology, so there's a lot of people that have already used in the past. The disadvantages is that it's low energy density compared with battery systems. So it's high density, but not so high compared with battery, for example, car batteries. Very high idle losses. For example, this means that, for example, if you charge these flywheels and you don't use the energy, so after 3 or 4 days, you might lose all the energy. So it starts spinning. Maybe after one day you lose 80% of the energy. After 3 days you lose 40%, and then it gradually loses the energy. Even given that it's in a vacuum, spinning at very high speeds, and you have magnetic levitation, it still loses energy with the time. So this technology is used if you need storage all the time. For example, hourly, 1 hour, the other hour you need to store energy from 1 hour to another hour, and you're using it frequently. Is a good alternative. Need for bearing maintenance and power of emerging magnetic bearings. So you need a lot of maintenance because you have a lot of spinning material, spinning things, and and as many spinning things that you have a high operational costs, even with magnetic bearings. Unexpected dynamic loads of external shocks can lead to failure. So the motor increases very rapidly the speed of the metal and you store energy. But for example, if you increase very rapidly and then decrease, it could happen that the system might break with rapid changes in power demand. The different types of flywheels. You have the mechanical one that I mentioned. Is supported by balls and rollers, leaves. You have the magnetic one, which is suspended by magnetic power, and you have a hybrid one, which is has both mechanisms. The magnetic one can be a passive permanent. The passive permanent is used with ultra. So is a particular material nowadays which it has very high, very low resistance, which usually you have to lower the temperature to minus 200, you know, to, I forgot exactly the technical number, but I'm going to talk this forward in the next slides. Active is basically you have to create a magnetic force, so you have to spend electricity in order to create a magnetic field with rods, so copper coils. You can create a magnetic field, but you have to constantly feed electricity, which reduces the efficiency. Oh yeah, so this is the one I was talking about. Superconducting material. Superconducting material, you don't need to spend so much electricity, and it's going to support the system and levitate it with low energy requirements. Some of them you have to lower the temperature a lot in order to reach this superconductivity material, or someone which are new technology with materials that at high temperatures you reach the superconducting characteristics. Um, yeah, so there are different characteristics, each one of these. You have the superconducting bearing is very expensive because the materials that composition of them is very expensive, but they give a lot good performance. You have the highest strength and of the materials. The the best is the cost, so you have to focus on increasing the strength. I'm not sure what switch to reluctant machine is. I'm sorry, I have to look it up. So there is a company called RevTerra which is already selling this high temperature superconductive material, and they compare with other technologies for flywheels, and they say that after 24 hours of a fully charged flywheel with their technology, you only lose 5% of the energy, which is incredible. So mechanical bearing, the ones that have that are not levitating, they lose around 75% of the energy after 24 hours. Lithium ion batteries, it's equivalent to this flywheel technology, but of course, lithium ion battery, you can leave the energy there for a month and it's going to still be charged. So this 24 hours only applies for this one, Of course, if you store energy with lithium-ion battery after 24 hours, you get the same efficiency, but it's not limited to 24 hours. You can store with lithium-ion batteries for longer. And the active magnetic bearing flywheel, which is the one which is a hybrid version of this heavy terra, it shows that you lose half of the energy in after 24 hours. If you don't use, you just lose the energy. And this technology has several benefits. For example, very fast speed, low power, so you have low losses. It's compact, so very energy dense. You can use for several hours, and it's more robust than the other alternatives. And comparing the efficiency with other energy storage technologies, you have the lithium-ion batteries. Here, they for some reason is the same company. Here, they show that lithium-ion battery is 85%. This VTR is 70, 95%, has 60%, and flow battery 70%. And I found a nice paper showing a comparison of these different types of flywheels. And for example, the power capacity that they store varies from 5 kilowatts, so very small uh, prototypes, to 2.4 megawatts. This is the amount of power that stores. So, for example, if you have a wind turbine that with 2.5 megawatts and for some reason it's not being used, you can use all this power generated in order to store energy. But of course, it's not gonna take very long, and you'll have your all your energy capacity filled up because the energy storage, the amount of energy they can store inside, is low, very low, and it's quite expensive actually. This technology compared with other ones, and I'm gonna go through the reasons in the next slides. And the speed is rotation per minute. So is 1,000 rotation per minute, can go up to 10,000 rotation per minute. Some of them 45,000 rotation per minute. The highest here is 40, 45,000. So huge velocities. Some ABB has 1,800, which is the smallest. And the smallest is 1,500 with pillar. The efficiencies are relatively high, and self-discharge is the amount of energy that you lose if you don't actually consume the energy. This is the amount of energy that you're slowly losing if you don't consume. So you store, you have to consume very quickly. So nowadays the energy density varies a lot depending on the design of the flywheels. And in 2030, the density is not really expected to reduce so much. The costs are expected to reduce, but for example, compared with lithium-ion batteries, which the cost today is around 200 US dollars per kilowatt hour, this technology, let's say in 2030, assuming that it goes to $1,000 per megawatt hour, is 5 times more expensive. So it's not a good solution for energy storage. Energy storage is not good for flywheels. Good thing for flywheels is to store peaks, very very short peaks of electricity. So you have because the power capacity, the cost for power for storing short amounts of energy at short amounts of time is low. So that's why I'm actually talking about flywheels. I'm gonna go through more detail. The lifetime is expected to increase, and compared this is in number of cycles, storage cycles, in number of years, it could reach up to 25 to 40 years in 2030. And the depth of discharge. So if you're using it at the highest efficiency, The depth of discharge will vary, for example, from 90% to 75% of the stored energy there. So it's always expected to be spinning. The idea is that you get advantage for the inertia of the system, of the spinning of the system. So you would always be operating at the best capacity around this energy storage. If it goes too low, it will then take much longer for you to start to charge it again, very fast speeds, because of the fact that the speed is to the power of two. So round trip efficiency varies from 85 to 87%. And this is for it is an example of another technology, another company that's selling flywheels. And I'm going to compare now with other technologies, for example, CAS or pump storage. So I'm going to focus mainly on the most important aspects of flywheels. So there are several informations here. For example, the cost of power cost, capital cost, in order to get the power to store energy to produce power is relatively low compared with pump storage compared, so it's almost the same as pump storage. You have CAS, but the problem is that you can't build a pump storage site in a house or close to a photovoltaic plant. Also, you can't install a CAS plants everywhere, anywhere you want. You can, but it's not going to be the most efficient ones. The good efficient ones, you need those salt caverns that Hannah explained in his lecture. So the cost per capacity is not so high, which is good. The cost per energy storage is 100 times higher than pump storage, which is terrible. So the idea is not to store energy, but to provide and store power, to store power and provide power. And the best characteristic of this technology is the response time. So, for example, pump storage takes something like the 60 seconds, 2 minutes, 20 seconds in order to reach the full storage capacity. So from not storing to start storing, it takes 20% in order to reach the maximum capacity for storage. But for flywheels, for example, is 0.25 seconds. So in 0.25 seconds, you reach the maximum capacity for storage. This is the main reason why people will invest in flywheel. Ultracapacitor has a even smaller, but I'm gonna talk about ultracapacitors in the next slide. So compared with batteries, you should use much more times these flywheels. For example, if you have a very repetitive service in your industry that you use energy very every 15 minutes, you need a burst of energy. Flywheels is very good because you store energy for this 15 minutes, you produce a lot of energy. This is an example. For example, for solar panels where you have a lot of clouds. So in a day, you expect it to generate a little bit of energy, but it's going to be very intermittent, extremely intermittent. So flywheels will make sense. If you want to store energy for 5 hours, for 1 hour, then you forget about flywheels, you go for batteries. Flywheels is if you want to store energy for 5 minutes, 15 minutes intervals, which is not always the case, but that's if you need that. If that's what you need, flywheels is the best option. And the motors can be asynchronous, can be variable reluctance, and permanent magnet synchronous. I am a chemical engineer, really. You guys are mechanical engineers. You understand much more than I do about these motors. I'm not going to go through so much details, but if you see the costs of these motors, they're quite low. They vary a little bit. The cost of flywheels at different references also vary significantly. So it's very complicated in order to find the data. I guess the main reason why is because there are some flywheels they are designed in order to produce cheap power storage. They focus a lot on the power. Some of them want both. They want cheap energy storage and cheap power storage. So then what happens that the power costs increase a little bit because they want more storage. But in the future, we expected to have only very cheap power storage because we already have batteries which have a uh, much lower energy storage costs. So the advantages I'm going to leave here. If you guys want to go through more details at the different generators and comparing the different costs also in the future with lithium ion battery and vanadium. We have, for example, pump storage is not going to vary so much. Flywheel is expected to vary even further because energy storage needs are increasing a lot, and flywheels has its own niche for energy storage, which I'm going through this lecture. However, is not going to compete for long-term energy storage for, I mean, not long-term, but 4 hours, 6 hours, 8 hours energy storage with lithium-ion batteries and all other batteries. This graph also shows the cost, which shows that the energy storage cost is extremely high, but the power storage cost is very low, lower than pump storage in this case, lower than CAS in this case. So also depends on the company, on the design, if the company has a lot of money to invest, which lowers the cost of the products also. So different references showing different things. This beacon power is an example of power plant. So energy storage power plant with flywheels. So each of these blue buckets are flywheels storage facilities. They are, in this case, dug under the ground in order to reduce the risks. For example, if one explodes, it's going to affect the others. In order to reduce the vibrations because it's spinning at extremely high velocity, so you have to be as stable as possible. If you have some vibrations, it can increase the chances of breaking in pieces. So this is another picture of this 40 megawatts flywheel project. So you can store 40 megawatts of electricity. It's in the state of New York. And it's very funny that once they got the investment, the money to build this power plant, the costs for annual frequency regulation prices. So in Brazil, ONS has a frequency regulation market, which they have some high altitude power plants, like for example Barra Grande in the Uruguay River. They they don't generate 100% of the electricity, and they throw away 5 to 10% of the electricity in that they could generate in order to provide regulation service to the voltage and to the frequency of the electricity in the grid. So they don't generate electricity, but they provide ancillary services. The market for ancillary services in New York until 2008 was increasing, was expensive, and then they built this plant, capable of removing these very small fluctuations in the grid. And then the cost of this ancillary service went extremely down, and probably they are the only ones providing the service because they're most competitive technology. And so this is a very interesting niche for this technology is for ancillary services for balancing the frequency of the grid and voltage of the grid power. Another niche for this technology is solar energy. So for example, if you are in a cloudy day and sometimes you have some moments where you generate a lot of electricity, so you have these huge jumps in solar power. What you can do, you can use a battery in order to provide energy storage, but you have two problems with batteries. One, a battery requires uh, so the battery, if you increase the voltage very high and then you lower the voltage, then you have these huge changes in voltage in the battery. What happens that the battery is going to lose its lifetime. So a battery that you might expect to use for 15 years, maybe you have to change after 7 years because it's not designed in order to absorb these extremely high changes in power generation, solar power generation, and voltage also, which is also involved in solar power generation. Or another scenario that you can use is if you have a very sunny day and you have a little some clouds, which it will very quickly lowers the solar power generation. So in a location where this scenario for solar power generation is common, flywheels could be considered. If you have a solar power generation in the Sahara Desert, which is extremely constant amount of energy, then batteries would be extremely will solve all your needs. I found this very interesting paper, um, which is still on show today by Elsevier. If you put flywheels energy in Elsevier, they select the most important papers on flywheels, and they show that 1980s they showed that flywheels substantially improve the efficiency of solar power generation, and inverter increase the efficiency of inverters, reduce the chances of inverters breaking. And it's very interesting if you want to look through. I mean, if you want to work in the solar power industry, it might be interesting to go through how this work. Before the inverter, you generate electricity in solar panels. The solar panels are connected in series in order to increase the voltage. And then you can either store the energy in batteries or in flywheels. If the energy, so the idea is that the very high fluctuation, very small, very short time high fluctuations are stored with flywheels, and in the long term, so the flywheels make the power supply more linear, so with not much noise. Then you can either use a battery in order to store a constant supply of energy, or you can go through the inverter and produce alternative currents. So yeah, there is an example of system like this, and they use solar power plants with 11 kilowatts of solar power plants, and they installed 11 kilowatts mechanical flywheel that can store 11 kilowatts in the flywheel, and a battery with 10 kilowatts hour. So the battery would be able to store 1 hour of solar power generation, a little bit less than 1 hour then of solar power generation. This is another example, and this is even more relevant than batteries because this is operating photovoltaic cells with fuel cell. So the problem with fuel cells is that the hydrogen is much smaller than lithium, for example, and it doesn't have uh, electrons. So electrons makes the lithium molecule huge, but an electron is a proton. Sorry, an ion. Hydrogen ion is a proton, and it's very small, so it's very difficult to be able to pass the hydrogen through a fuel cell. And if you have very high volatile fluxes of voltage, what happens is that you're going to damage your fuel cell even faster than you damage your battery, or the ramp up reduces the amount of energy, so then you lose energy, you reduce the efficiency if you have very variable solar power generation. So flywheel also is used in order to increase the efficiency of PV and hydrogen generation. A good place to see if a paper is saying something that is actually important is Alibaba. So you see, okay, I read this paper and stuff. Oh, let's see if the market thinks that if this makes money. So I put solar power flywheel energy storage, and there are several several products that you can buy in Alibaba, which gives an inverter which has its own flywheel technology, but it's very small. It's just to in order to reduce these peaks of solar generation. But new inverters come with their own flywheels. So what I'm talking here is not that you're never gonna hear it again. It's already being sold by China. Another example of this flywheel and solar technology is is built in, I think it's in Denmark or in the Netherlands. Is a combination of a solar power plant generation with flywheels. So they're doing the same thing. They're just making sure that the supply of electricity is constant. They're increasing the efficiency of the solar power plant. So the thing is that you might have a 100 megawatt solar power plant. You might need only 5 to 10 megawatts of flywheel capacity in order to remove completely this the variation in solar power that you come out of your solar panels. So it improves the quality of the solar generation that you have. But now looking at wind power with flywheels, there are several papers, but one paper I found that shows that is not as important because the wind it varies a lot, similarly to solar irradiation varies. But given that a solar tower already has its own rotational mechanic system, it already is moving the generation from wind energy because these turbines, the wind turbines, they are huge, they are heavy, and they have high inertia. So, for example, you have a gust of wind, very strong gust of wind, is not going to have a peak in wind generation. It's just going to contribute to slowly increase the generation of wind, and then it's going to slowly reduce. So this slowly increase and slow reduce, it's okay for batteries, for example. Batteries can easily deal with these slow variations of changes in wind power. Wind power and um, flywheels doesn't make so much sense. Doesn't make as much sense as solar power. Any questions so far? Right. So talk about the grid inertia. So the ONS and most grids around the world are used to having turbines generating electricity, and these turbines they get in synchrony with the frequency of the grid, and if the grid frequency for some reason reduces, the motors get designed in order to reduce their speed, so the inertia of the spinning of the turbines, they will contribute to maintain the frequency of the grid at, let's say, 60 hertz in Brazil, in the US, or 50 hertz in Argentina or Europe. But for example, solar panels don't have this inertia. wind turbine, as I mentioned, has a little bit inertia because you can reduce this, you can absorb more energy from the spinning turbines, but not as much because it could be the case that for some reason the wind stops blowing. For this case, you have batteries and inverters can do this easily, but for solar panels is the main issue. So it's as if an example here, this picture trying to explain this, you have one spinning rod connected to several power plants, and all the power plants have to spin, generate electricity at the same frequency. But the problem is that with solar power, the amount of money that you need to spend in controls in order to achieve this high quality generation frequency is not so easy. You can spend a lot of money and improve the quality, but then you lose efficiency, and it becomes more expensive, your solar generation. So there are several ways in order to make sure that this works well. So the challenges, for example, is if you have a black start, you have a blackout, for example, you need to start your motors again. And if you don't have inertia in the motors, it's very complicated, very expensive in order to turn all the system back again. Another challenge is, for example, the intentional islanding. For example, some substations, some locations in the grid of a city, of a whole grid have different frequencies, which are not incompatible with other regions. That this could also create blackouts. You have unintentional islanding. So, for example, you have a lot of solar power generation in one location, you don't have so much in other location, which could cause issues with the frequency of the grid. So, this type of problems. So, in the past, we had a lot of coal power plants, hydropower, nuclear power plants producing a lot of inertia to the system. So, for example, if you had a you reduce the frequency in one part of the grid, one of these turbines, which spin at very fast speeds, they will lower a little bit the speed in order to achieve the same frequency, while they come up with other solutions in order to increase the amount of power to the grid. But, for example, new solutions, they have very low inertia. For example, the worst case is PV systems, inverters, also batteries are also not a good example for inertia. They don't produce so much inertia to the system. So they are good solution for energy storage. But for example, if they don't enter at the right time and the frequency lowers at a certain point, then you have a blackout. So this is an example. If you have a grid and one power plant blows up, and then you reduce the amount of power supplied to the grid. If you have a turbine loses a blade and stops operating, all the other turbines which are spinning, they will have enough inertia to lower the impact of this fault in the system in the frequency of the system. And then, of course, you have to add other solutions like energy supply from batteries, or you turn up other power plant, or you increase the generation from a flexible gas power plant, and then you go back to the frequency that you have in your target. So grid inertia is very important. There are several other challenges. For example, transient and dynamic stability, um, frequency regulation, the voltage regulation. These are challenges which you have if you don't have inertia in your system. Grids with high share of renewables lack inertia. You have weak and unstable grids. Increase the rates of change of frequency. So, for example, if you don't have inertia, the frequency is going to go up and down like crazy. The imbalance of load and generation causes frequency excursions, and the consequences are no contribution to support the grid with extra temporary active power, no enhancement in frequent support, and high risk of load shedding and grid blackouts. So it's a problem that we have in the future, grid inertia. And solutions for energy storage for grid inertia, for example, comparing flywheels, batteries, ultracapacitors, and fuel cells. Solutions, of course, you have pump storage, which is similar to a hydropower plant, which is great. So we don't need to talk about that, but of course, you can't build anywhere as. So compressed air energy storage is also a solution which you have a turbine spinning at very high speeds, which can create inertia, but also has it doesn't make sense in every location. Flywheels do. So you can put a flywheel in your garage. You can put a flywheel in your supermarket, close to a substation. For example, you have a substation which blacks out all the time because the frequency goes crazy, and then you put a flywheel there, then this will reduce the chances, the risk that you have blackouts. You can put flywheels close to solar power plants to improve the quality of the electricity that you provide to the system. And the most important aspect you have is the response time. The response time varies from 5 milliseconds, depending on the design of the flywheel, to 250 milliseconds. Batteries, for example, are the response time. So the amount of time that takes for you to generate at maximum power capacity is very low, 20. Ultracapacitors, 16. Fuel cells is a little bit higher because it's more complex. But the problem is that the current that you have in flywheels, you can have an AC motor or a DC motor, or in generator. But for batteries, ultracapacitors, and fuel cells, they produce electricity at DC, and but then you have to go through inverters, and the inverter response time becomes around 1 second, which is terrible. So, for example, if you really want to provide inertia to your system and guarantee that the frequency balance with quality, and you don't have a power plant, you don't have a hydropower plant, you can use flywheels for this service. So the advantage of flywheels, they reduce voltage fluctuations in the charge and discharge of batteries, including increasing their lifetime. They are good option for frequency and voltage regulation in the grid. Just a comment here, you have that a frequency of 60 hertz means that in every 16 milliseconds you have one cycle. So one cycle of the power grid, whether you have the voltage reaches 120, for example, then goes minus 120 in Brazil in 16 milliseconds. I put seconds here, but it's milliseconds. Just for you to have an idea how fast the response rate has to be in order to control voltage. So this is a video. Let's watch a video about this. Somebody else giving another perspective and talking about just to conclude this topic, and then we'll go through another topic. You guys might be almost asleep there. I particularly don't think this subject is so interesting, but I try to make as interesting as possible. I'm sure with a nice video you'll find it.
Stornetic, the energy storage company. Stornetic, the energy storage company. The future requires an optimal utilization of energy and secure access to environmentally friendly electricity. Here at Stornetic, we support a better electrical power supply. Stornetic is a driver of innovation and as such offers demand-oriented energy storage solutions with flywheels. They are manufactured using the latest production methods with the support of extensive experience with high rotation rotors and tested safety concepts. With it, electric energy can be stored efficiently, quickly and consistently as mechanical energy or fed back into the grid. Stornetic, a European company. With N-Wheel, we set new standards. We make use of one of mankind's oldest tools and optimize it for an entirely new purpose, the storage of electrical energy. The N-Wheel consists of casing, a carbon fiber rotor, a motor generator unit, and a solid base. Speed is the key to efficiency. The carbon fiber flywheel accelerates to 45,000 revolutions, hovers wear-free, held by magnetic bearings inside a vacuum. Electrical energy drives the flywheel up to highest speed. The so-called stored kinetic energy is transformed back into electricity with minimal waste. The flywheel storage can be loaded and unloaded without any aging or wear. DuraStore combines several N-Wheel to a system solution. The modular structure allows expansion and the creation of customized solutions at any time. DuraStore contributes to grid stabilization via frequency regulation and displacement of peak loads. The grid's voltage quality is monitored, problems with voltage are balanced and grid utilization is improved. Fluctuating supply of renewable energies also influences reactive power within the network. The DuraStore electricity stores react to voltage drops and shortages and thus contribute to the regulation of electricity distribution. The DuraStore power stores help generators of green electricity to raise their own contribution. Energy distribution is improved, the network stabilized, and energy costs are reduced across the entire value chain. Energy can be used more efficiently in industrial plants. DuraStore is better able to balance out peak loads and ensures interruption-free electrical energy supply. The operating power is not lost. DuraStore is a turnkey system solution, especially when it comes to the supply of new sources of electricity production. The frequencies are regulated within the shortest amount of time. Microgrids are stabilized and a supply according to plan is enabled. Integration of renewable energies and the progress of electrical mobility present a challenge for electricity networks of the future. The Stornetic flywheel store enables a reduction of the network load via quick and secure charge and thus resolves disturbances within the network. Self-sufficient microgrids mostly consist of conventional production in combination with renewable energy production far away from big supply networks. A quicker network balance is then required for network stabilization. DuraStore stores electricity and is able to release stored energy when required at short notice until other sources of production ensure network stability long-term. If, for example, a disturbance interferes with the energy supply, DuraStore balances out supply and demand with stored energy again. Even in case of varying power feeds and fluctuating consumption, the energy store balances out voltage fluctuations within the network. Energy supply remains stable and the primary energy need diminishes. Thus, expenses are reduced and the environment is saved. Stornetic ensures reliable and affordable electricity supply in the 21st century. Stornetic, the energy storage company.
Right. I hope you guys enjoyed the video. So this is flywheels. They have a much shorter storage cycle than batteries. As you can see, it was going up and down like crazy because it's not designed to store energy for more than 5 minutes, 10 minutes. That's the conclusion. Any question about flywheels, energy storage? Okay, so let's talk about gravity energy storage. So gravity energy storage is also very similar to pump storage. Not in The only difference is that instead of storing energy with water, you store energy with weights. So you have different weights that you pull up and down in order to store energy. For example, you have gravity energy storage, which when you lower the weights, you produce electricity. When you bring it up, you store energy. It's literally the potential energy equation. So, any potential energy that we learn to pass our vestibular is exactly how this process works. And you have another one, which is buoyancy energy storage, which you have something that's very light, for example, air in a balloon, and then if the balloon rises, you're generating electricity. When you pull it back, the balloon, then you store energy. The equation is the change in height per second. The change in height per second, and you have the weight, which is the mass of the object. I delete it here. Is the mass of the object in kilograms. So this is the amount of energy that you generate, and the amount of energy that you store is the height where your mass is stored times the mass times the acceleration of gravity times the efficiency of the system, which is around 80 to 90%. So this is the power capacity, how much power you generate. It depends on the speed in which the weight is lowered. So if you lower really quickly, you generate more energy. If you lower slowly, you generate less power. Sorry. If it goes quickly, you generate a lot of power. If it goes slowly, you generate less power. Energy storage is how much weight you have still up there in order to be used. So technology that has been developed and proposed, and a lot of people are talking about this, is gravity, which uses old mining shafts. For example, in the UK, in Australia, US, there are several mining activities, which is deep mining, which instead of having open pits, very large pits of mines, they don't want to open these pits because it might be it might have a large impact on the environment, or because the resources that they want is, let's say, 100 meters down, and it doesn't make sense, financial sense, to make 100 meters deep pit mine in order to start extracting the coal, for example, 100 meters down. So there are several thousands and thousands of these deep mines, underground deep mines, which are not being used because they were decommissioned and they don't operate anymore. And they can be used in order to store energy with bringing this weight up and down. So the idea basically, when you have a lot of wind power, you have solar power, you run these, you use the electricity in order to pull this heavy weight up. And when you need to supply electricity to the grid, you lower this big metal thing cylinder. For example, there is each unit would have a capacity to store a potential power capacity to store up to 20 megawatts peak hour and can take a duration of 15 to 8 hours in order to rise. Of course, depends on the diameter of the cylinder the mine pit, the hole that you have. Depends on the weight of this mass. If the mass is very long and very heavy, if you put lead is expensive, so maybe not lead, but you use a material which is deep and very heavy, you increase the amount of hours that you can store because the the mass, the cylinder will store more energy because it's heavier. And the other thing that contributes to increasing the amount of hours that you can store with 20 megawatts but power is the depth. So, for example, if this mine pit is 300 meters that deep, then you can store three times more energy than if it was 100 meters deep. This also comes with the benefits of flywheels, for example, because you have this spinning mechanisms which are connected to generators, to motors, which if you're careful enough to make it very sensible to power changes, you can use it for grid inertia, for example. You don't need to have a huge power plant, or you don't need to have a huge pump storage site, and you can provide inertia with this system also, similarly to how I explained with flywheels. This is a picture of uh, several sites where they have these pits in the UK. So the UK had several of these mines, and they have several open pits. So these holes in order to reach the mine. So they had a lot of coal in this region, and they had a lot of several of these holes in order to reach the coal. And these are potential sites where, with not so much investment and money, you can put one of these gravity systems. A study from Imperial College showed that the cost of this system is comparable with is cheaper than flywheels. It's comparable with lithium ion batteries and the amount of energy storage. So the cost of storage itself is they don't even put the cost of flywheels here because it's 20,000. It's extremely expensive. But compared with, for example, with lithium, this price is expensive. This might be a bit old because nowadays it's $200 per kilowatt hour. I guess this is for a Powerwall, Tesla Powerwall. Maybe this is the price for Tesla Powerwall today. But they say that gravity is much cheaper because the cost for the energy storage is the weight of this cylinder. And if you make this cylinder cheap, then the energy storage is going to be cheaper. This part is the power capacity, how much you can discharge and charge the system. So this is the power costs. So these are related to power costs, and the energy storage costs are just the cost of the weight you're lifting and reducing. Of course, this cost also considers that the hole that you're using already exists because it costs a lot of money to make a hole in the ground. And then they compare with a figure, the same similar values. Oh no, this is the levelized costs. So this is the cost of storage itself. And then if you remember that I put that equation, I have this cost of storage, capital cost of storage, investment cost of storage. Then you have the levelized cost, which also take into account the O&M costs and losses, for example, investment. So, well, they argue that is a cheap alternative. let's watch a movie. I guess it's a good way to get a nicer feeling. So these alternatives for energy storage is worth talking about, but they are not very complicated. It's just lifting a weight. So I don't need to talk so much about it, but it's also good to look at nice videos, flashy, because they spend a lot of money doing these videos, so might as well give them some credits.
Renewable energy production fluctuates throughout the day, as does demand. We need to store excess energy when the wind blows or the sun shines so it can be released when demand outstrips supply.
Okay, I forgot to share the link. I guess you guys can put this gravity there. But sharing the link now. Sorry, forgot.
Already we can store energy using pumped storage and with batteries. At Gravitricity, we have a new idea. We can harness the power of gravity by using excess electricity to winch a large weight in a vertical shaft, which can then be released, turning the winches into generators. The shaft can be up to 1500 metres deep with a weight of anything from 500 up to 3000 tonnes. The heavier the weight, the more energy is stored. Raising the weight charges the system, whilst lowering the weight discharges the electricity back to the grid. After all, what goes up must come down. A typical system would power over 13,000 homes for 2 hours. Or, sophisticated winches and control systems can lower the weight very fast to deliver shorter bursts of very high power. It's this flexibility that makes Gravitricity unique. For example, electricity networks need to stabilise the grid at 50 Hz. Gravitricity is well suited to this because it can respond with full power in less than a second. Our technology has the fast response times of lithium-ion batteries, but unlike batteries, it can be charged and discharged again and again, many times a day for up to 50 years, with zero degradation. This means we can deliver a range of energy storage services at an affordable price. Analysts at Imperial College say Gravitricity can be the cheapest form of storage in the global fast frequency market. Now we're building a 250 kilowatt concept demonstrator in Scotland, which will be connected to a simulated grid. This will be followed by a full-scale commercial prototype in a disused mineshaft in northern England. There's a huge global opportunity in existing mineshafts, and we're planning early systems in South Africa and Australia, as well as Europe. Once the technology is proven in mineshafts, we will also sink purpose-built shafts wherever superfast, long-life energy storage is required. For example, near to towns, factories and renewable energy installations. Gravitricity, versatile, long-life energy storage.
Right. So this is Gravitricity. Literally, it's very similar to flywheels, but has the advantage of storing more energy, has a cheaper energy storage cost, and yeah, the video explained more or less what I had told you before. So if you have questions, please ask. The other the other design, which is very similar to, which is not very similar, but similar to Gravitricity, is to have these shafts, but they are enclosed on the upper part and on the lower part, and this piston is floating on the water. So and if it's at this position, what happens is that fully charged. And what this piston does is increases the pressure of the water in this section. And this pressure exerted by the piston would allow electricity to be generated from this pump. Uh, And if you need to store electricity, then you would need to lift the piston. You have to pump water from this section to this section, and in this way, the system that it requires for the power generation is a pump with water, which is very efficient, which exists several pumps, centrifugal pumps. The main issue is to find the shaft which you can put a lot of water, because water is wants to escape, and the deeper that you go, the higher the pressure, and very complicated dynamics. This is another option, but personally, I don't think it's a good option and might never happen. I'm just going through some examples. I don't think it's worth watching this video. So this is Ares, which I have read several papers and things about this, but for some reason I forgot what Ares means. I'm gonna uh, have a look here. What it stands for: Advanced Rail Energy Storage. So the idea is to have a rail with tracks and like a train, for example, and below a mountain you have storage sites where you put these weights. And what you do is that you store energy by picking up these heavy uh, concrete blocks, and with electricity, these tracks will go up. And then when you are generating electricity, you bring these blocks down, and with this you generate electricity. The main challenge and issue with this technology is that with tracks and with a curvature, what happens that you have a lot of friction losses with friction. So the efficiency of the system could be as low as 30%, 40%, and it's expensive to build these rail tracks and to find a efficient way in order to store a lot of these concrete blocks. So there has been in history several people trying to propose energy storage solutions like this, but none of them ever worked. There are some prototypes in the US, one or two, but it's quite expensive. An alternative for this is the Energy Vault, which is this tower, which I think is worth watching also because it's a really nice video. If you guys haven't watched yet, it's worth watching. So I'm gonna put the link here for you to have a look. It's a different example for energy storage solution. Gravity based energy storage. I'm sorry the video didn't have an explanation. Or should have put a video with explanation, but it's a
We are in
nice,
the opening stages of a massive paradigm shift in how we manage and utilize.
a nice representation of how the system works. And the idea basically is that when it's fully charged, you have the tower like as high as it can get. So you have all the blocks making a tower which can reach 200 to 300 meters depending on the location, and the tower rebuilds itself, lowering these concrete blocks and becomes something like this. So the height difference between the lower base and the central cylinder, the central tower, reduces, and then it doesn't really make more sense in order to lower more the tower because you're not going to make so much electricity. So you stop at this point, and then if you charge, if you need to store energy, what happens that system with AI, artificial intelligence, which is clever enough in order to rebuild this huge tower, would with electricity bring this um, concrete blocks back into the position and store energy. I'm going to talk a little bit more about this because I wrote a similar paper about a similar idea. And yeah, the cost of power is involved with the amount of guindastes, né, that you have, and the amount of cables and the amount of motor generators that are used to bring the weights up and then storing energy and and lower the weights, generating electricity. And the cost of energy storage is the cost of the concrete blocks. The more concrete blocks that you have, the more energy you can store with the system. So energy storage is not too expensive. It's not extremely cheap because these concrete blocks are not 100%. It's not very cheap, but they are not so expensive also. And there is a paper talking about this technology compared with other technologies, saying that the capital cost is for the is capital cost per energy storage is quite cheap compared. So the concrete blocks is cheaper to store energy with concrete blocks than with lithium ion batteries, for example. However, the cost of the cranes, the cost of the cables, the cost of the equipment for power is expensive. So the idea is that this system would have to operate for 8 hours, 12 hours, or maybe 25 hours. And the idea is that you have to use the energy cycle longer. You don't need a mountain, you don't need a pump storage site, you can build it anywhere. One issue that I see with this technology is that, for example, if you have a storm, it's very windy, these concrete blocks are going to be going like everywhere, and you won't be able to control them and rebuild the plant, which is not a good thing. For example, if you're storing energy, wind energy, and then it's windy, and then you can't store energy because it's windy, then for wind power it doesn't make sense. If, for example, you have maybe solar power, it makes sense. For example, I don't know, you're in a location where it's not very windy. So a lot of people invest money in these technologies. They might have to think twice before you invest money in a technology which will never make sense. But there are a lot of people investing in this, and the inventor is very happy and making a lot of money. So if you want to compare with other technologies, this is the graph. I'm not going to go so much in detail. I wrote a paper about gravity energy storage, and I call it mountain gravity energy storage. So the idea here is that you don't need to build your own tower. You use a mountain uh, in order to use the difference in height. So you don't need to build your own mountain. You use a mountain that exists, and you bring, for example, sand, and you have two storage reservoirs, and you bring the sand from the lower reservoir to the upper reservoir, storing energy, and when you need to generate electricity, you lower the sand in these buckets, in these storage vessels, and then you store energy. I'm gonna go through a little bit more detail on this paper. This is the image that Yaza created for the press release, because they created a press release and there was a lot of interest. A lot of people contacted me about this technology, showing a little bit more how it works. We have that the vessels, they will go under the sand or gravel storage sites, and you have these control valves that will fill up the vessels. You have to be careful because this system has to be constant, so the speed in which the vessels move are always the same. So this system, this releasing system, has to make sure that it gets all the sand very quickly in the bucket while it's passing through. You have a loss in heads, so the efficiency of the generation is from the height that the sand enters in the system compared to the height in which you dispose the water, the the sand in the system. So when you're charging, the height difference is from here until here. When you're discharging, the height that you have to calculate to estimate the amount of potential energy that you have is from this to this, which lowers the efficiency of the system, because you have the sand has to go through this storage site, which lowers the maximum head of the system. So you have a bit of a head loss here, and of course you have other losses in the system with friction, with, for example, the speed. When you go up, you have a drag from the winds, several other losses. I created a model which uses the topography of the world with 50 meters resolution, and I created a methodology to look at the potential capacity of the world. And it shows that, for example, the highest potential is here in the Himalayas and in in um, in the Andes Mountains. This is an example for an island in Hawaii. If you can see the color where is more is the lighter blue and red, is the location where you have the highest difference in height. The steepness is the highest. So this model is very simple. We just look at the difference in height from this pixel with the lowest pixel around the 4 pixels. So north, south, west, east, which one is the lowest shows the potential of this technology for this pixel. And this is an example that I use for this island. I'm gonna explain in the next slide why I chose this island and an island. This is the topography of the location. So the technology potential varies with the highest difference in height in 90 meters resolution shows the best place. So for the case study of the paper, I chose particularly this region because you have an area large enough to build your storage site in below. You build the above storage site, and also has a good height difference. I created an example of operation assuming a given demand that varies daily, and I have the amount of energy storage in the system, and the generation is the amount of electricity generations provide both with wind and solar, only wind and solar, and you have the mountain gravitational energy storage and batteries. So the idea of this system, it's to work together with batteries, and the mountain gravitational energy storage will provide a long-term energy storage solution, so seasonal storage, while the battery will provide the short energy storage cycles. So, for example, hourly storage. So the battery it charges, discharges 3 or 4 times per day, and this Mountain energy gravitational storage, it's continuously increase or decrease. So this provides the seasonal storage. And I'm gonna explain in the following slides why. So for this system, the energy storage costs, so the cost for energy storage is very cheap because it's sand, and sand you can buy $1 per ton from Egypt, for example, is the cost that I assume for my paper that I have to estimate the cost for the project. Sand is very cheap. It's much cheaper than concrete blocks. So a concrete block is something like $50 per kilowatt, 50, $30 per kilowatt. Sand is 30 times cheaper than concrete block. So with a concrete block, it would not make sense to store energy seasonally with this technology. But sand, given that sand is so cheap, this technology makes sense to store energy for a long time, for a month, for a year, for maybe more than a year. And the main cost, the most expensive part, is this tower and the motors and equipment in order to generate electricity and store electricity. Similarly to the tower, as I explained to you, as I showed you. Um, so why would you invest in this gravitational energy storage, this mountain gravity energy storage? The idea is to have, for example, large energy storage cycles. So from 7 days to up to 3 years of energy storage. So have very large energy storage cycles. So you want to store energy for seasonal, several months, but the capacity of the system, so the amount of energy that you need to store is less than 1 megawatt to 10 to 20 megawatts. Why? Because for pumped storage does not make sense for systems that with 1 megawatt. With 1 megawatt, pumped storage is not viable alternative. So you cannot build a large instead of filling up a reservoir with sand, you could fill up a reservoir with water. And but the problem is that first you might not have water, and the other problem is that in order to make the pipes viable, so pipes the higher the diameter of the pipe, so you increase the diameter of the pipe by one, you increase the amount of flow that you have to the square of the diameter. So pump storage is one of those technologies that have huge gains in scale. The larger the plant, the cheaper it gets. The smaller the plant, the much more expensive it gets. So given that gravitational energy storage does not require pipes, require just cables. The cables they can be modular. You can put several cables, or you can increase the thickness of the cable. You can provide systems that are viable with very low and a generation capacity. So this is one of the papers that I published, which already has something like 20 citations in 2 years. And for some reason, I just found it interesting, but everyone's citing it, and it's very good. So there are several benefits. I showed the scenarios, different locations, and I tried to explain why this location is better than the other. I estimated the costs with data from Alibaba, and I tried to make some assumptions. And of course, the best I can get. This is the cost. I created the cost for this mountain gravitational energy storage, and it shows that is 4 times more expensive than 2 times more expensive than pump storage. Yearly storage cost is uh, twice the price, maybe 10 times higher, depending on the project. And the capacity varies from zero point 0.5 megawatts to 20 megawatts, and pump storage has a much higher capacity. Of course, the higher the difference in height, for example, if you have a height here of 2,000 meters, so in the top of a mountain, then it becomes cheap. The capacity, the energy storage, the more, the higher the difference in height, the cheapest is the energy storage. The lower, for example, if you have only 200 meters difference, then it's gonna become 10. It's gonna be 10 times more expensive. The system with the same amount of sand. So it's very sensible to the difference in height of the system. It's one of those things. This is a video that you might want to watch. It's been the prototype that Bill Gates created with this technology. However, he focused on hourly and daily storage. He doesn't have this idea of seasonal storage. Of course, a battery is gonna be much cheaper in order to store energy for 6 hours, 12 hours. So these systems doesn't make sense for a daily storage. Just makes sense for monthly and longer storage cycles. Another option, which is very interesting, one French guy said that he was working on the project when I did this, which the project was to use these lifting cable uh, ski resorts. So during the winter, these towers, these cables, they're used to bringing people to the top of the mountain to ski. But in the summer, no one uses, and usually it's there when and no one's using. So what he proposed and what he was developing, he has a company doing this. The problem is that I deleted my emails from Yasa because the my storage emails were full, and I deleted everything, and I forgot his name, and I can't find his paper. Very interesting paper. The idea is to change these during the summer, these chairs to vessels, and on the top of the lifting station they have streams with rivers, and they will fill up these vessels with water, and the system would in the summer, when the all the ice melts and starts melting, locations where you have streams on the top of the mountain, you can generate hydropower. And the advantage of hydropower with cables is that you can have up to 2000 meters heads, so huge heads, because it's not sealed in a pipe, so the pressure doesn't go very high. It's just water in the bucket, and then you bring the water down in the bucket, like people used to do pump hydropower in the past, and it's a suitable technology. Another option is to have several sites where you fill up these vessels. For example, in the mountain, maybe you have a stream in the middle of the mountain and another stream in the top of the mountain. So then you can fill up the vessels at different altitudes. Hydropower, you also always have a fixed head. So the water comes down in this head and comes out in this head. You cannot put water from different heads, because if you try to put the water at this head, the water is just gonna not gonna allow to go in. So very interesting proposal. For example, somebody who is trying to build ski resorts, they might be able to think and generate hydropower also with the system. In his paper, he cites some mining companies which are mining on the top of mountains, and they do the same. It's, n- it's not energy storage, but they generate electricity and they lower the minerals with these towers with cables. And while they lower the cables, instead of having brakes, which are also expensive and high maintenance in order to brake and lower the speed of this system, they put a generator, and the fact that you generate electricity, the generator brakes and lowers down the speed in which these minerals come down, and you also generate electricity. So in the case studies that he showed, they have mines on top of mountains that not all only extract minerals from the top of the mountain, but they also generate electricity. So very, very interesting project which exists. So in the last 40 minutes, I'm talking about things that doesn't exist. So this exists. Other examples for buoyancy. So talking about more on the buoyancy side, you have balloons on the bottom of the ocean where you can lift and then generate electricity. By doing that, as I explained in the beginning of this section. I personally was writing a paper that was about five, four years ago, I started writing a paper about I called deep ocean gravity energy storage. So the idea is to have a vessel where it supports because the vessel is floating on the ocean and is supporting all this weight. And then the idea is to lower the weights and generate electricity while doing that. And then when you need to uh, charge your battery, you pull it up. So this is so the cost for power is in the ship for pulling is similar the cost with the other systems, and the cost for storage is the concrete blocks. And I shaped the concrete blocks as a triangle because on the ocean under the water you have a lot of drag, so drag is much higher under the ocean than on the atmosphere. So the idea of making this shape, because when it's coming down, the drag caused by lowering this reduces. So then you can reach higher velocities and thus higher power in order to generate electricity. And when you're bringing up, you have the same problem. You also have drag. So also I shaped this as a cone in order to reduce the drag. And I made some calculations and estimated that the power varies with speed. If you don't have drag, if you increase the speed, it would be a straight line. However, with drag, you have that you increase speed, you have to, it reaches a point that you have to increase much higher the speed in order to generate the same power output because of the drag under the water. Another option, instead of putting weights, you can put balloons, and balloons are quite handy, quite nice because the pressure inside is the same pressure as outside. They will have to rise in volume because the volume of the air will expand if you lower the pressure inside. But the interesting thing is that at different depth, the ocean goes down. There are locations far from the continental shelves, easily reaches 6,000 meters deep. So 6,000 meters in order to generate electricity or store electricity by lowering and rising things, it's an interesting alternative. For example, if you are in an island or in Hawaii and you don't want to put your turbines on your mountains because it's going to spoil the view, or you don't have enough space to supply all the wind that you have, you can put an offshore wind turbine, floating offshore wind turbine, and use one of these systems to store energy. The advantage of using these balloons is that the balloon will supply the lifting capacity to itself because air floats. So the ship that you have wouldn't have to be a huge ship in order to support the weight of these concrete blocks. So the cost of the ship is going to reduce. You have to make sure you make a balloon that's resistant enough. And another French guy is also working. So French people love this gravitational thing, and he's developing this prototype. It also has a nice video here, and he claims that a block of concrete under the ocean stores the same amount of energy than 100 Tesla batteries, and the cost of this block is $7,000, and the cost of the Tesla battery is $320,000. He mentions that this is only the price of the blocks. You also need the cost of the equipment to lower and to rise the block. So this might increase to 200,000 $200,000 instead of only $7,000. So, but he shows some equations. He shows that it's much more competitive than batteries. Another advantage is that the cost of the concrete blocks is cheap. So energy storage is cheap. So instead of storing energy for 12 hours, you can store energy for 25 hours, 48 hours, which, for example, if you want to store energy from wind power, you might want 78 hours storage capacity, kind of like the initial amount of energy storage that you need to remove the intermittency from wind generation. So concluding the lecture, we have that flywheels is cheap alternative for storing power. Flywheels are already used to increase the lifetime of batteries in solar power systems. Flywheels can be used to increase future grid inertia, future renewable grid inertias with a lot of solar panels. You don't have anything spinning to guarantee that you don't have blackouts. You can use flying wheels. Gravitational energy storage is a new alternative with good potential. Underground water energy storage could be used for storing offshore wind power energy. Thanks so much, guys. Any
Thank you,
questions?
Julian.
Any questions? Any? By the way, I received your inputs, your projects. So thank you so much for staying until the end. This subject was a little bit not the most interesting one, but I tried to make it interesting. I hope you guys liked it. I'm gonna write more papers about it because it gave me a lot of citations. So if you're interested in working on a paper, also let me know. That deep ocean gravity takes me probably a week to write, so it's worth writing. Okay, no questions. Thanks, guys. See
Thank
you
you,
next
Julian.
week.
Bye bye.
Bye.
Very nice. Thank you.
Bye bye.